Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, thanks for coming. Today's speaker is Romain Thibault. He's a candidate here and coming to us from UC Berkeley, where he's working in Michael Jordan's group on bringing statistics together with computer science. He did an internship with us in MSR a couple years ago and is now finishing his PhD. Thanks, Romain.
Thank you. All right, so it's working. So thanks you all for coming, and thanks for all the people watching on the MSR channel. So the big event in my life is I just got a baby recently. So you talked about my PhD being finished, but that comes second to that. And so I'm going to talk about the work I've done for my thesis, and this is work as Emery said, at the interface between statistics and computer science. So I'm more of a computer scientist by training, but I spend a lot of time in statistics department, and I'll try to convince you that that's a good idea and why I'm motivated to do that. So what's going on between these two fields? You have computer science that's about 50 years old, and that the one thing that's been really good at is data structures. The kind of things that people get really excited about when they start computer science is trees and graphs and all that. And computer science has been really good at how to handle that kind of data. Now statistics has been good with uncertainty, probabilities, how to make decisions in this kind of situations. But the kinds of objects that it's typically handling is real numbers, find the mean, or random vectors, etc. So we want to do statistics, deal with uncertainty, but over objects that are more complicated, like the kinds of objects that computer science deals with. And machine learning can be thought of as the name for that growing intersection between the two fields. Whoops. So one tool that we have to try to bring these two together is the use of Bayes' theorem, Bayes' rule, that says that your posterior distribution is proportional to the likelihood times the prior. What that means is for typical models, the traditional models in the statistics, if you have a parameter that's, say, a real number or a real vector, you have, do I have a pointer? Let me find a pointer. Otherwise, I'll be tempted to point at my screen. All right, so you have prior distribution, represent prior belief about your hidden parameter that represents the structure that's hidden in the data. And by factoring in the evidence given by your data, you get an updated belief of posterior distribution over your parameter. Now, nonparametric models, nonparametric Bayesian inference is about doing the same thing, but with more complicated object. A stochastic process, you can think of it as an infinite dimensional random variable. So it can be, I'll give some examples of that. And so the kind of complicated things that you can, that fall in that category of stochastic processes are things like trees of unbounded depth and unbounded fan out. And that's pretty new, that you can deal with this kind of objects in a probabilistic way. Partitions, we'll talk about that. Infinite binary matrices, we'll talk about that too, and distribution. So each of these objects, not only do you have to define what these objects are, but you have to define distributions on those objects. So particular distributions on distributions. So there's a lot of work on how do you even talk about these objects? How do you define mathematically? And then how do you manipulate them? What algorithms do you have to do inference? And what kind of applications can you do? One way to use these objects for applications is to build Bayesian hierarchies where these objects are going to be embedded in larger models. So here's the kind of applications that have appeared recently that use these kinds of techniques. And here I give some examples in different fields: vision, biology, natural language processing, and all of them have in common that there is a very complex structure that's hidden in the data that's hard to capture by modeling it as, trying to capture it with just one number or a vector. And all these applications at the core have the Dirichlet process that's been really the star of this field. The Dirichlet process gives you an infinite collection, random infinite collection of probabilities, they sum to 1. And from this, you can obtain random partitions. So if you now have observations that are your data points, data items, or whatever they are, you're going to sample from that random distribution. And here we're just going to put a 1 if that item chose that particular choice that was given with this probability. So you choose one of these categories with the probability given what the Dirichlet process gives you. And what this does is it gives you a distribution on partitions, because here what this says is that y1 and y3 are together and y2 and y6 are together. Using partitions in computer science for algorithms is not new. You can use k-means, you can use agglomerative clustering, things like that. So clustering is not new. But what's new is that you can put now a prior distribution on clustering. You can talk about a distribution on the number of clusters and the number of clusters can grow as the data comes in. And this is with an unbounded number of clusters. The fact that you have a distribution on it means that it becomes possible now to embed this in larger models and use probabilistic inference. And that's what all these models that I showed before, all these applications rely on. So the Dirichlet process came about in 1973, was defined there and used for some applications in statistics. Some of the important extensions or related processes were developed a little later on. In particular, the stick-breaking construction, where you have the first construction of the Dirichlet process was not constructive; it was just theoretical. And here you had an explicit construction for the Dirichlet process, and that's been used a lot in algorithms. And really, the breakthrough is in '95, where Escobar and West realized that this Dirichlet process is not just a distribution on distributions. Really, what it gives you is a distribution on partitions, and that's really the why this has been used in all of these applications. And then since then, a lot of algorithms have been used that have been developed that use many of these properties that have been discovered before. Along the way, a number of fields have merged into that line of research. People working on genetics using Kingman's coalescent and the Ewens sampling formula. They realized that was related to the Dirichlet process. People working on infinite permutations and distributions on infinite permutations is very related to the Dirichlet process. And all of that was used to design better algorithms. So all of this revolves around the Dirichlet process and around partitions. But partitions is one thing that, one kind of structure that can arise in data, and we want to move beyond that. So I'm going to introduce another object called the beta process, and that's going to model all the other kinds of structures. So the beta process is a little similar. It's kind of the evil twin of the Dirichlet process. You have an infinite collection of probabilities, also random, but it doesn't have to sum to 1. And the way you are going to use it is, and I'm going to define what the beta process is more concretely a little later. But the way we're going to use it is we're going to say that data points or items, whatever you're modeling, have that feature or belong to that group with probability given by the height of that stick. What the kind of structure that it gives is a set of attributes. That's another kind of structure that's familiar to computer scientists, but not much in statistics. And so, for instance, the kind of things that this could model if you're modeling clients of Amazon. Maybe this one means I'm interested in electronics, and this one means I'm interested in cooking and things like that. So the relationship between clients is far more complex than just a partition. I share some features with some people, but I share other features with other people, etc. All right. So beta processes, before I can really describe what that is, I need to describe an even larger family of things called the Lévy processes, of which beta processes are part of. And really, Lévy processes is a source for the beta process, but also other processes, like the gamma process I'll touch on briefly. And all of those have a potential for being used for models in machine learning. So I want to describe the whole family. Any questions before I go there? So the one Lévy process that a lot of you are probably familiar with is the Poisson process. It's the simplest one, and it's also a very important one. How it works is you have some intensity function, and you draw a set of points here on the line, but it can be on more general space. What the rule is that the number of points that fall in some interval of some set A is Poisson distributed with intensity, the integral of the intensity function on that area. The other way to write the same thing is to talk about distributions. And I'll use distributions a lot, so I want to make that point clear. You can say the same thing by saying, so a distribution is a function that gives mass to sets. You give it a set, it gives you a number. And here, the mass of these, instead of a set of points, you can think of it as a distribution that gives mass the number of points that fall in that set. Same thing with this intensity function. The mass that it gives to a set is the integral of that intensity. So the intensity measure is the integral of that intensity function. So here I'm just writing the same thing, but in terms of distribution. And the key property of the Poisson process is not that much that it's Poisson distributed, but if you have two disjoint sets, the number of points that fall into the two sets is independent, and that's going to be a key property. Okay, so I want to spend some more time explaining distributions because I'll use them over and over again. This is just an example of the Poisson process on a more general space. So discrete measures, which Lévy processes are. Yes, question?
I'm sorry, I didn't understand your notation that you were showing there. Can you repeat that return? Yeah. So n. So you have n on the left hand side, on the right hand side. And there's supposed to be two ways of representing the same thing.
Yes.
It's a function. So n of a. Could you just what are the semantics here of the
yes.
right-hand side?
Okay. So n is a measure. So that means if you give it a set in this space, it gives you a mass. It gives you the mass that this measure gives to that space. And the mass that it gives is how many points there are in that space. Sorry?
But A, so n is okay, I understand n, but A is a distribution.
No, A is a set here.
So what's a distribution on the right hand? What's the difference? Can you repeat the difference between the
So A is a set, n is a measure. N of A is how much mass n gives to A, so that's a real number. And that real number is distributed with a Poisson distribution with parameter f of A. A again is a set, f is a measure. So f of A is how much mass f gives to A. How much mass f gives to A, that's this integral, this gray area.
The difference in notation, like on the
I'm just trying to understand what's written here. So what's capital F?
Capital F is the integral of little f, thought of as a measure. So it's not the integral from 0 to a point. It's you give it a set. So you can if your sets are just intervals, f is a function that if you give it the lowest point of your interval and the highest point, it gives you how much mass is the integral of little f on that interval. Yeah, please ask questions because that's going to be important. So n is a discrete measure because it's right. It's so capital F is really the integral of little f. N is a measure, and you could think of it as a function. The integral of a function that would be 0 everywhere, except at those points, and yet it has integral 1 just at that point. So you can't obtain that with a function. I don't know if that helps. But so that's why you have to be a little more general and go to talk about measures. So measures are, if you are familiar with probability distributions, then probability distributions are just distributions that happen to have a total mass of 1. So if you have mass that's not just 1, then it's more general. So here is how we are going to represent discrete distributions. We're going to say, okay, there's a mass of 1 in each of these points, so we're going to put a little stick of size 1 at this position. So let's call omega that space. Here the real line could be more general. And little omega is the location of that atom. And so this point is omega I1. And again, the mass of a set given by this discrete measure that's drawn in red is the sum of 1 for each point that falls in that set, which you can write as the measure is the sum of Dirac delta function or point masses at that location. And the slightly more general version is you can have any arbitrary mass for these atoms. So these points, let's call pi the mass of that atom, and the mass that falls into a set A is now the sum of the masses of the points in there. And this is just a weighted sum of Dirac delta functions. So now we're almost there to describe Lévy processes, because Lévy processes are discrete measures such that the amount of mass that falls into two different sets is independent. In other way to say it is, if I'm struck by lightning, that doesn't tell you my neighbor that whether he's any more or less likely to be struck by lightning. Okay, you can be a little bit more general to describe Lévy processes, but I'm going to leave it at that. So that's the definition of Lévy processes, but you can actually construct them explicitly. So the Lévy-Khinchin theorem says that a Lévy measure is characterized by its Lévy process is characterized by its Lévy measure. And the Lévy measure is, so here's the space omega on which we want to define our Lévy process. And we're going to have a Lévy measure on omega cross R. And that will allow us to draw at the same time because it's a random discrete measure, so that means you're going to have random locations for the atoms and random heights, and you want to draw them jointly. Yes?
I mean, just the difference between Poisson process and Lévy process is just the discretization with a version of Poisson process is the Lévy process. Is that right? What's the exact? Well, how would you differentiate between those two processes?
So if you have imagine you have a Poisson process. So Poisson process gives you atoms of just mass 1. Now you can imagine you have a Poisson process with atoms of mass 1, and then you add to that a Poisson process with atoms of mass 2, and then a Poisson process with atoms of mass 1/2, etc. So you're going to get lots of points and with lots of different masses, and actually you can construct Lévy processes by doing what I'm just saying, by adding lots and lots of small Poisson processes, each with
independent Poisson?
Yes, independent Poisson processes.
It seems like you should be able to get a Lévy process by having like the probability that a half spike is somehow related to the probability, the density. You know what I mean? The density of the half spike is somehow related to the density of the 2 spike, and they don't have to be independent.
No.
Yeah, okay.
So wait.
At one spot,
yes.
The density of a half spike doesn't have to be, could be related to the density of the 2 spike. They don't have to be.
If you use a Poisson process with a continuous intensity measure.
The x's could be related. You're saying.
Sorry.
What did you call the f of x?
The intensity measures.
The intensity measures could be related between
the intensity measures could be related, but if they're continuous,
right,
that means you have probability 0 if you draw 2 independent Poisson processes of falling exactly, of 2 atoms falling exactly at the same spot.
That's what I was asking, but I think
okay.
I answered my own question.
Okay, all right, so good. All right, so where was that? This Lévy measure, here is an example. So that's, I'm drawing the intensity associated with that measure, is a measure on R cross omega. You draw a Poisson process with that as intensity measure. And now if you look sideways, this is the same kind of pictures that we had before, where each point here is a location and a mass. So if you just draw the stick, this is the same picture as before. And again, the mass of a set in omega is the sum of the masses of the atoms in here.
How do you choose PI?
How do I choose what?
PI, the weights.
The PI? So PI and omega I are jointly drawn from the Poisson process with this intensity. So this is, think of the Poisson process and the intensity of the Poisson process as how much cloud there is here, and these are raindrops, and they just fall randomly depending on how much cloud there is. And in particular, it's possible that this Lévy measure goes to infinity next to the axis omega, and in that case you would have an infinite number of points here that would still be okay. The mass can be finite, because if they're very small, then this sum, even though you have an infinite number of terms, can still be finite, and the beta process will be like that. So I'm ready to introduce a beta process. Yes.
So the picture that you drew, it seems like nu is independent of omega. Is that right?
Nu is a fixed quantity. So nu is not random.
Sure, but it's the same.
Yes. Right. So that's a good point. Here I'm drawing an example where nu, that's right, is some function times uniform on in that direction. You don't have to have that, right? It doesn't have to be.
So it's actually, mu is actually just defined on R.
So
Well,
you
it's this,
right.
it-
So here, yes, you can be more general and have any
Okay, good.
intensity on R cross omega. That's a good point. It's just harder for me to draw. But you're right too that Lévy processes, when they were originally defined, were only processes of that type, which I would call now uniform Lévy processes, and that makes things a little easier. So the beta process is a special kind of Lévy process. I need to define what its Lévy measure is, and that's its Lévy measure. It's all complicated, but I'll show a picture of what that looks like. But already, so it depends on two parameters: a real number called the concentration and a measure, B0, and that's a measure on the space omega. Here you can see at least that part of that expression of the Lévy measure has a form, if you're familiar with the beta distribution, that looks like a degenerate beta distribution, hence the name beta process. Now, something I didn't say earlier I should have in Lévy process is that if you construct it with the Lévy measure, you can't have atoms that fall twice. If you draw several times, you can't have an atom that falls twice at the same position. If you want to have that, if you want to have fixed atoms with random mass, you can add that in too. And there's a way to factor that into the Lévy measure, but let's not go there. So you can have that with beta processes. If your base measure is continuous, you have this Lévy measure. If your base measure has atoms, then these atoms are going to be beta distributed. And again, hence the name. All right, so here's a picture of what this Lévy measure looks like. This is the same kind of, so again, here I'm assuming that the measure B0 is uniform. And so as I said, it goes to infinity here. This measure is not integrable, so I'm going to have an infinite number of points near the origin. So here's an example draw from that. And again, if you
So you're setting the alpha parameter or the A parameter of the beta to 0. Is there a reason why? I mean, you're not using the full power of the beta.
That's right. So if you, I'm not sure if I would say full power, but the points. So here I'm drawing a picture where B0 is uniform. If B0 has atoms, is going to be beta the atom will be beta distributed with, this is a general beta. So you can have atoms that are beta distributed in a more general way.
Or do you have to fix it to be p to the -1 in order to get a finite measure? Is that why you go p to the -1? You don't put another parameter in there.
So why is there no extra parameter?
P of b -1.
Right. You would get something quite different. In particular, you would get a finite. Then this function would be integrable. Mm-hmm. You would get a finite number of.
It'd be like a bump.
Right, and you would get a finite number of atoms, and I don't know. That's a good question. I should think about what that does. That's a little different flavor. All right. So what do you do with the beta process? So you do the thing I was showing before with this grid. You have a number of observations, a number of items, and you're going to draw. You're going to say, I include this. So let's call this space omega a space of features. You're going to include this feature with probability given by the height of that stick. What's important here is that. So let's see. Apparently there seems to be a little problem if you want to do that concretely. If you want to draw these points, you first have to draw B, the beta process. But that's an infinite object. There's an infinite collection of points, so you can't sample that, you can't represent that fully in the computer. But there's a method to sample the first line directly by marginalizing out this guy, and then sample the second line conditionally on the first one, and so on. And that process is called the Indian buffet process. And it was actually described by Griffiths and Garamani before the link with the beta process was understood. So here's how it goes. You imagine that you have an infinite buffet with an infinite number of dishes. And customers come in one after the other. That's going to be our items. And customers are going to try a number of dishes. The first customer tries some number of dishes, and that's the features that this item has. Customer 2 makes a decision whether to try the same items or not of the previous customer, and then makes a decision also how many new dishes do I try. So the general rule is after n customers have come into the restaurant, the n plus first customer decides whether to eat a particular dish with probability proportional to the number of people who have tried it. So there's a rich get richer property. The more popular, the more you're likely to try that. And the C parameter appears here. That's the C from before. And then you try a Poisson number of new dishes with some parameters. Gamma here is the total mass of B0, the measure we had before. And this Y Poisson number of things, that's related to the fact that Lévy processes have a Poisson construction with the Lévy measure. All right, so the Indian buffet process, so when this is an example where I just continue this process for a long time, and you see what it looks like. So this picture doesn't quite look like the picture I had before. This doesn't look symmetric, but this is only because I've ordered the picture, ordered the features in the order that they were first discovered, that they were first tried. So if I shuffle the order of the columns, then it'll look the same. And a lot of applications have emerged of the Indian buffet process because it gives you a possibility to have distributions on attributes for data, and now all of a sudden you can do all kinds of different things that you could do with the Dirichlet process. So one question you might ask is, if all of those use only the Indian buffet process, why is it important to know that there's the beta process that's underlying all this? So here's why. So at a high level, the historical note for why this is important is that the Dirichlet process also has the same relationship with another process called the Chinese restaurant process. That's the equivalent of the Indian buffet. And about half of the algorithms that we know to handle this pair, Chinese restaurant process and Dirichlet process, rely explicitly on the Dirichlet process. So it was clear to me before I went after the beta process that if I understood what was behind the Indian buffet process, then immediately I would have a lot of the same things that would fall from this connection. And indeed, you get a size-biased construction. That is, you can construct the beta process in the order in which features are found by the Indian buffet process, and that's very useful for inference. But I won't go into that. Gives you an algorithm to sample beta processes, and people before that were using beta processes for other kinds of things and survival analysis, and they need to do that, and they were using more more difficult algorithms. And the things I'm going to talk about is hierarchies of beta processes that really you can't do without using beta processes, and I'll touch on new models of data. All right, yes?
So I'm not sure if this is a good time to ask this question, but can you elaborate a little bit on this rich get richer property of the beta process?
Yes.
I kind of understand how that works for Dirichlet processes.
Yeah.
You basically get the size of the clusters that you get look like a power law, right? Because that's what the rich gets richer scheme gives you.
Actually, the size, it looks like it's decreased exponentially. The size of for the Dirichlet process and for the beta process, the size of the sticks, if you order them by their size, that's going to decrease exponentially fast. But to answer, so your question was why? How does this property of rich get richer come about? Where does that come from? Is that your question? No.
What is this property? What does it look like for a beta process? What do the sizes of the clusters look like?
Oh, what are the sizes of the? Okay, so what is the distribution? Right. If you look at the stick sizes, just the stick sizes, not their location, what that distribution looks like.
So if I want to use it to model user preference at Amazon, categories of user preference,
Yeah.
how many people do I expect to? So what's the, I guess what's the distribution of the number of categories? So
Yes.
I think you touched upon that.
Yeah.
And also how many people like each category?
Okay, so here's some answer to that. Whoop, here it is. So you know that the first customer tries a Poisson gamma number of dishes. By exchangeability, which means that the order of the rows here doesn't matter, we know that each person has a Poisson gamma number of dishes that they're going to try on average. Not on average, that's the distribution of their number of dishes. And depending on C, the concentration parameter, the number of dishes that they're going to eat as a whole, that they're going to, as a whole, have tried after n customers. So it's going to be logarithmic in C. Sorry, the logarithmic in n with some coefficient depending on C. And if you push C to 0 or infinity, you can make everybody try exactly the same dish. You just have one Poisson number of dishes for everybody. Or you can have nobody shares any dish. Every new customer tries a new set of dishes. So it's logarithmic. And another way to answer your question is if you, in the special case where C equals 1, the stick sizes, too bad I don't have a, let me be all fancy and use this. Whoops. All right. So the stick sizes of the, it doesn't work, right? Okay. Here are the stick sizes of the Dirichlet process. They sum to 1, so this is a stick of size 1. And the stick breaking construction, the thing that Raman found in '94, says that you're going to cut that stick with a beta proportion, and then cut the remaining stick with a beta proportion, and then cut again and again and again and again and again and again and again, etc., with beta proportion, and you get an infinite number of sticks that just decrease exponentially. Well, so this is the stick, this is stick number 2, etc. It turns out for C equals 1, there's a weird connection with the beta process where this is the first stick, this is the second stick, and this is the third stick, etc. So you have exactly the same underlying mechanism to generate the sticks of the beta process. That's something that E.Y. Tay has found out. So it gives you an idea also of how fast these things are decreasing. All right, so I'm going to go to hierarchies. How much time do I have left? Not much, like 15 minutes, all right? No.
We have the room until noon, but usually talks
Oh, okay, all right, so that's okay if I'll go a little bit over. So hierarchies. Here's what our hierarchy looks like. We start with the same as before. We have a beta process, which gives us heights of sticks, and we sample points from that beta process with Bernoulli. But the base measure B0 of that beta process is going to be itself drawn from a beta process. So in particular, that means that this base measure B0 is discrete here. And so now we're in when I defined the beta process, there was one case is using the Levy measure, one case is if you have atoms, you have a beta distribution. Then that means we're in here on the second case. For each atom of B0, there's going to be an atom right under it in B, and it's going to be distributed with a beta distribution with mean pi0. So why would you want to go there? Let's see. Okay, this is just to say that the mean is pi0. So the mean of B is B0, if you will. And C control, how similar B0 and B are. So here's the kind of things that you can do with that. So let's say you want to do text modeling. You represent documents as the binary vectors of which words belong to that document. And you want to predict what does the next document what will the next document look like. Why would you want to do that? For instance, if you do classification using naive Bayes, you want this going to be the likelihood with which this document could belong to that category. So really what you're trying to get at is for each word, if you assume words are independent, for each word, what is its probability? So you're trying to get at what is the underlying beta process that tells you all you need to know about this set of document with the probability of each word. Now imagine that this is only one category and you have other different categories. For each of them, you would like to know what is the probability of each word for that particular category. But of course, these are related. If the word the is very common here, it's likely to be very common in that category, etc. So if I want to predict this document, this next document, all this data, even though it's not from the same group, it tells me something about that document. There's some information. So what we want is, here we could use an Indian buffet process to represent the sequence of documents and the features they have. We want a set of related Indian buffet processes. One way to do this is to use a hierarchy of beta processes where you have a sort of master beta process that gives the average set of probabilities for each word, and then these are drawn from this one. Yes?
So Kamal-Nagin suggested the same kind of thing, but not in stochastic processes, just with multinomials. I don't know, does it work better? I mean, have you tried it empirically?
With multinomials?
Yeah, he had a hierarchy of multinomials with a fixed, because there's a fixed vocabulary of words that you just observe, and then he just sort of traversed the hierarchy and got some improvements. But I don't know if have you compared it?
So maybe this is I'm not familiar with what you're referring to, but maybe this is similar to what is done with the Dirichlet process. But the Dirichlet process is associated with a multinomial. Also, you draw from that process different words, and you can have a hierarchy of Dirichlet processes, and that's been used a lot.
So he used a multinomial to kind of smooth, in other words, to kind of smooth out or to generate new multinomials for each category. In fact, it wasn't just one level; it was sort of n levels.
So is it a fully probabilistic model, or is it?
He was. I don't know. I don't remember. It's been a few years, but have you tried it? I mean, I don't know. How well does this work?
No, I mean I've tried this, but not the one you're referring to.
How does this compare to, I don't know, any of the other ways of doing?
So one thing you can compare to is so when you're doing naive Bayes, the typical way to predict these probabilities is, first idea, you try maximum likelihood. That's saying you try to take just the empirical probability for each word, And of course, that doesn't work at all because some words have, never appear, so you predict them to have 0 probability. So instead, you use Laplace smoothing, which adds some pseudo counts to, you pretend that you've seen this word before, and you pretend you have not seen it before a certain number of times. They can be a fractional number. And so that's used very commonly, but that uses only documents from that group, that discards entirely data from the other groups.
Well, people use Laplace smoothing that are prior taken from the universe.
From the universe.
Yeah. So if you say, gee, because that's just a beta prior. It's just a beta prior on that word, right? It doesn't have to be 50. It doesn't have to be 51.
Right. Yes.
Yes, you choose some variance, but we don't know, but it has to do with the number of final counts. People do that. That's pretty common. So I don't know.
So it has to do with?
Oh, you just compute the frequency of all the words in the universe. Like how often does the word the occur in all the documents?
Okay.
And then you use that as a smoothing term. You know what I mean?
Okay.
So if it doesn't occur in the word, you could just smooth back towards the commonality you have.
Okay. So it's slightly different. One way in which it's different is that here you are smoothing towards the mean of these probabilities, not the overall mean if you bunch everybody together. So for instance, if you have a category, this category is very large, and this category is very small, in this averaging, this category is going to have the same weight as this one. Whereas if you average the probability over your whole data set, you're going to count this one much more. That's one version. I don't know. I haven't tried.
Oh, okay.
And another aspect is that this is a fully probabilistic model, so it's much easier to combine with other, build high-level hierarchies.
Well, except that
cetera.
these won't give calibrated probabilities because there's still an independence assumption between words that isn't correct. So that the P of sports given the set of words that you see won't be a calibrated probability. You can't really use it for very much anything unless you recalibrate. Because
So
there's an unwarranted independence assumption between words.
Yes, here we're considering using naive Bayes, where it's known that the classification accuracy of naive Bayes is pretty robust to this bogus independence assumption between words, but of course the probability that it returns is not to be trusted. But if you want to, if you have many different categories and some of them are related and they're related in a tree, for instance, that's going to be harder to do. It's going to be harder to do the right smoothing. Here, if you have a hierarchy, you automatically, using probabilistic inference, get the right number at the end. So
I'll show you a couple of papers.
Okay, yeah.
How does this compare to hierarchy diversity processes? Performance.
Right, I don't know. So I was trying to think what you would use the Dirichlet process for here, but you would then code the document differently by counting the number of, by basically having the number of the counts for each word, and then using a hierarchy of Dirichlet processes. I would compare. This is compared to Laplace smoothing. If you want to predict the next document in a particular category, the first category, this is the log probability of the next document obtained on test data. So that gap is pretty big here. It's that gap means is you give about 60% more probability to the correct answer on average than if you use Laplace smoothing. So the fact that you are doing better at predicting the new documents for a category should mean that you should be able to do better at classification than if you use Laplace smoothing. And indeed, on 20 newsgroup data set, if you use hierarchies of BP, you do better than naive Bayes with Laplace smoothing. And here I should say that the comparison is try to make it a little bit unfair. I've chosen the parameters of the beta processes based on principal, and then one parameter based on cross-validation. And so this is just one number on unseen test data, whereas here I've basically done a grid search on all the parameters and looked for on the accuracy on test set that was the best one, and the best one was 50%. So there's no way to attain the level even if you knew what parameters to use. Yes?
Is it categories of size 2 to 100? I mean, the version of 20 newsgroups I work with had 1,000 messages per category. Is this just a different variant of
yeah, this is something I wanted to experiment with different sizes of categories. How does that affect things? And
this is again using what they call what Andrew McCollum calls Bernoulli naive Bayes, not multinomial naive Bayes.
That's right. And in a second, I'm going to extend that. So how do you do inference in this? I'll briefly say. The key property of Lévy processes that allows you to do inference is that since all of that slice of the hierarchy is independent of that whole slice of the hierarchy, you can do inference separately here and separately here. In any partition that you choose, you can do inference separately in it. In particular, you can choose the partition that puts each individual atom, wherever you have at least one observation, you put that, you say that's one set. And then you'll have one big remaining set where you have no observation at all, but that contains all the rest. And in here, this is just a hierarchy of real valued random variable. The mass of that stick, the mass of this one, and they have a hierarchy of beta distribution where pi is drawn from a beta distribution that depends on the one above. And what is the distribution of pi0? Interestingly, it's an improper prior on pi0. And when you run inference, so this is not a valid distribution. Nonetheless, when you run inference, because you have observations here, this becomes proper. And if you're interested in that kind of things, that this gives a concrete example where improper distributions arise, where they're used all over in statistics, but usually they're understood as a limit or as a sleight of hand or kind of approximation, a way of saying things. No, this is really what is the right distribution to use is improper. Now I want to move on to new models of data, new variants that you can derive from beta processes, unless there are questions. Yes?
So you mean that inference meaning inference of the hierarchy of P's that you're not observing?
Yes.
And you can do that separately for each word that is...
Right, for each, right. You can do separately for each word. That's what makes inference efficient, because when you're doing, say, naive Bayes, so naive Bayes is it's very fast when you use something simple like Laplace smoothing. It just counts, and for each word you just do a little count, and that gives you a score, etc. And here it's the same thing. For each word you can do a little reasoning among classes, but just considering that word and then move on to the next. So the complexity is the same.
But your hierarchy and the associated P's, they're not identifiable, right? Because what at the end of the day, what do you have but the count of, and the distribution of which documents occurred in what? But you don't know what's the actual topics. So you don't know, like for instance, how many levels of this hierarchy are there in actuality, and you can't identify the P's associated with them. So at the end of the day, I'm saying you still can, I have the same problem working with social networks. You can kind of build this model that contains this hidden hierarchy, and you can learn something like that. But if you can't actually interpret this hierarchy and say that this is actually the hierarchy that generated this data. You can only say that this gives me a likelihood that's, better than some other model.
Right. So here I think you're thinking of a situation where you have different categories and you're trying to do some kind of clustering. You don't know which documents belong to which category. Sure. Here I'm being much more restrictive. I'm doing classification. So this is, I know which documents belong to which category. This is supervised. And I'm really just trying to get a better smoothing for an A-based. So yes, you could definitely use these kinds of models to do what you're saying. But of course you have to accept that inference would be much harder because now you have, just like in many of those problems with that have Dirichlet processes, you have a clustering. When this clustering is not observed, you have to make inferences about that clustering. That's a big space, the space of possible clustering. So inference is hard. And here, I'm not sure so here P is definitely all the probabilities in that hierarchy. If you assume that this is the hierarchy that generated the data, then P is definitely identifiable if you have infinite data for each category.
So where does the category label come into your model?
Here that's a given that I'm given the category label. I'm not trying to infer. So I have labeled data for which I know which category they belong to. And I know which categories exist, how many they are, and all that. And I have some new test data, and I'm just trying to find for each of them independently which group they belong to. But I'm not trying to jointly group them together.
So here you know the number of
Yes.
atoms that this data process generates.
No. So maybe there's just a little bit of confusion because the atoms in the Dirichlet process are used for each atom that corresponds to one group. So if you have that, if you have that group, or if you are in that group, that's exclusive to all the others, and the game is, okay, who belongs to which group? Here, we are using the sticks in a different way to say, if I have that feature, if I have a 1 here, that means I have that feature. So the atoms do not represent clustering. Yes.
Well, in particular, so the classification of a new document corpus would be politics and science, right? You effectively you're going to.
All right. So here, okay, you're thinking of a slightly different model than I'm showing. Here, the features that I have or not are words. So I have the word bush and I have the word ball or something. But here, I'm assuming that you belong to only one class. You could use the beta process and the Indian buffet process in a different way, where you say there's a hidden category relationship, things like this talks about politics, this talks about sports, etc. And each document could have this aspect and have this aspect. And now that wouldn't be directly observable from your data. That would be something you have to infer. And so now you would have a distribution over who has which features. Whereas here, this is observed. We know which document have which feature. We know which documents have which words. It's a different use of the model. All right, so maybe I should move on. Keep the rest of questions for the end. Here are some models that you can, do once you have the beta process that go beyond what I've explained. So instead of attributes that are ones and zeros, as you said, you can go to different, more general attributes. So you want something like this, that you want some process and you want to be able to say that each document or each item has 2 of this feature or 3 of this feature. So think, for instance, if you're doing vision and you're trying to infer the existence of different features that images can have, like pedestrians and cars. Well, these things can appear several times in the same image. So it's not like I have pedestrian, I have maybe 3 pedestrians, etc. So in a model like that, you would want something that's able to represent that kind of uncertainty. So here are some options to do this. So let's see. Well, that's okay. So I wanted to. That's an example application where I need this. I'm doing image classification. That's recent work. What you do here is you compute some SIF descriptors. That's something that people in Vision have developed to describe a little area on a grid on the image. And you're trying to basically reduce to the text case. And for that, you need some kind of vocabulary, the equivalent of the word. And what you do is you take a whole bunch of SIF descriptors from natural images. You do a vector quantization. And then for each little patch, you then attach it to what is the closest vector quantization. And that gives you a vector of counts now for each image. I have this particular visual words a certain number of times, and this one a certain number of times, etc. Yes?
So what do you use that for? What's the application?
Image classification. So the same as the text, but with images now. And
what kind of class? Is it a generic, like outside, or is it?
Right. So I have 2 data sets I'm working on. The 15 scenes category, where you have 15 scenes that are outside, industrial, city, tall buildings, and things like that. And there's the Caltech 101 category, where you have 101 categories obtained from the web. Things like a horse and planes and cars and stuff like that. So I'm trying to categorize them.
Do you get any boost as compared to like LDA backup words? Like people have done the same thing with latent featuring.
Yes.
As well. Just getting a sense of.
So yes, they've done that, but it's not state of the art.
I thought this was one of the better. On Caltech 101.
I'm not sure which one is the best now, but the latest I know is doing better than the LDA I think you're referring to, and by good margin, and that was using support vector machines.
Yeah, but the way they do it is they use backup words. And then they train kernels on top of that using those backup words, which were trained using LDA. And that's the SVM version that you're talking about. So basically...
No, I'm thinking of different SVM, but maybe this one is... So the SVM version, I'm thinking of Lezebnik.
Yeah, the same one I'm talking about. They're using LDA backup words.
Okay.
So you can actually replace that LDA backup words with your backup words and do a same comparison, right? And then you can actually...
Okay.
I'm just
yeah. I'm surprised because they had compared their method purely SVM with a kernel based on these features to using LDA first as a preprocessing, and LDA was doing worse, but that's possible. Let's see. So here's the kinds of ways that you can have a probability distributions on attributes with general counts. We used before the fact that the beta process was conjugate to the Bernoulli process. That means they work well together. It turns out the beta process and the geometric distribution also work well together. And so you can have, for each stick, for each location, you can draw a geometric number of instantiations of that feature, and so you're going to have a general number. So this is here the size of the circle is proportional to the number of times you have that feature. And the geometric distribution has the shape which may or may not be what you want. In particular, 0 is always more likely than some big number, etc. And so here's another possibility. I haven't talked much about the gamma process. The gamma process is another type of Lévy process, and that's why I introduced the whole family. Use the gamma process, and it turns out the Poisson distribution is conjugate to the gamma, and so you can do all of those things. Now you can almost turn the crank, and you get a model for this kinds of data. And it's going to have different properties from the one before because the distribution of Poisson distribution looks like that. And it turns out this is the same as the beta process was the answer to the Indian buffet process. There's a recent model at NIPS on the Poisson gamma model, which is in fact the Indian buffet process. This is to the gamma process what the Indian buffet process is to the beta process. So the gamma process and this thing are related, although it's not obvious when you see it. And before I show compare to the support vector machine on images, I want to say a word about what generative and discriminative how they methods differ. And this method using naive Bayes is generative in the sense that you try to find a good model of data. You're not trying to optimize directly as discriminative methods do your objective, which is here classification. So you're not expecting to do better than discriminative when you use generative. But once you have a good model of data, this same model can allow you to answer many different questions, do things like anomaly detections or compare different which two categories are the closest and things like that. So here are the three different methods that I've introduced: beta geometric, beta Bernoulli, and gamma Poisson, and how they compare to the state of the art, which is SVM. This is preliminary in the sense that I'm not quite sure yet that the set of features is exactly the same between the two methods, but it should be fairly close. And really the thing that's not in the graph here, because they don't report it, is how much time it takes to run. Here we're talking about 3 seconds here and 3 minutes. This is a one versus all
train or to evaluate?
To do everything. Train and evaluate all at the same time. And this is a one versus all SVM. So this is the 15 scenes category, but you can see that this is going to have a pretty high complexity on something like the Caltech 101 data set. That means you have to run 100 times an SVM on all your data. So they don't report how much time that is, but I suspect that's pretty high. And the complexity is at least n squared and probably more. So in terms of the number of samples that you have, the complexity is pretty bad. And so that's the advantage here I'm presenting. And with that, I'll just conclude. I'm already late, so I'll just leave that here. Really what I want to say is I'm expanding the vocabulary of things that you can represent with probability distributions and manipulate and combine with other things. And it's been pretty successful with the Dirichlet process, and I want to expand it with other processes, other kinds of things that you can manipulate. And thank you. Okay, right.